We'll look at the supported MCAD platforms and then the processes that are available to yourselves. So the RoundTrip, so that's exporting from E3 through into MCAD and then bringing all of that data back into E3 and generating the Formboard. Outward trip then would be an example where your electrical engineers design the schematic in the connectivity, and then that's then passed to your mechanical department, who are then responsible for the formboarding. Outward trip with back annotation. So again, the mechanical department are responsible for your formboards, but then what we do is we take the length information back into E3. Okay, so there's no direct correlation with the harness, but obviously the connectivity and the wire length is available to you in E3. And then a return trip. So the return trip is where the work is started in the MCAD system, and we just import that back into E3. Then we have videos showing all of these processes, and then we'll look at any considerations that need to be made in order for this to function properly. So our supported MCAD platforms, so as we mentioned then, at the top we have CATIA V6 or 3D Experience, CATIA V5, SolidWorks, NX, Solid Edge, Creo, and Autodesk Inventor. So I did touch on the processes, and what we'll do now is we'll just take a look at a brief overview. So for a round trip, the connectivity or the wire or the connectivity information is passed to the MCAD system via a PLM XML file generated through our 3D routing bridge. It's then routed in the mechanical CAD system and transferred back into E3. So transfer the connectivity out and the topology back in. So there's a direct link to our schematics, and the electrical department takes care of the harnessing. So for our round trip, you see that all of our supported systems are capable of achieving a round trip. Next is our outward trip. So the outward trip is obviously the connectivity information leaving E3 and then being handled by the mechanical department. So once again, it's our PLM XML file, and that is transferred across to the MCAD system, and that's where the ECAD stops, effectively. So there's no direct link to the schematic, and the mechanical department will handle the harness or the formboards. So again, the outward trip is supported by all of the systems. Next then is our outward trip with the back annotation. So again, through the routing bridge, PLM XML file goes across to the MCAD. And what we do then is updating the PLM XML file, we then read that back into E3, and that will populate our wire lengths. So whilst there's no direct link to the harness, the wire length is available. So if you were to query any of your connections, you would see the physical wire length. So outward trip with back annotation is only supported by CATIA V5 and V6, Creo, NX, Solid Edge, and isn't supported by SolidWorks or Inventor. So finally then, our return trip. So a return trip starts in the MCAD environment, and it is then transferred into E3. So there is a direct link from the harness to the schematics, and it effectively is the electrical department's responsibility to handle the harness. Return trip then is only supported by the CATIA V5, the CATIA V6, NX, and Solid Edge. So as an overview, return only is supported by V5, V6, NX, and Solid Edge. The round trip is supported by all of our platforms. Outward is supported by all of our platforms, and outward and with the back annotation is only supported by V5, V6, SolidWorks, Creo, and NX. Okay, so obviously that was a very brief overview. So thankfully what we have then is we do have some videos prepared for us by our German colleagues who actually demonstrate how that works in real life. So the round trip, as I mentioned, connectivity is exported from E3, then goes into NX. 3D is exported from NX in JT, which is NX's native format. This is then read into our 3D transformer module, and from there we then extract the topology and flatten our harness. Once flattened, we can then write that directly to E3 as a formboard, and the flattened harness is available to you in E3. Okay. So if anyone knew this process previously, this used to be a multi-stage process using a number of modules. They've all now been combined in the 3D transformer. Okay. So as I mentioned then, first of all, what we need to do is we need to export our connectivity information. So in this schematic, what we have a number of connectors, we have splices, and we have an eyelet. From here, what we're going to do is, using the 3D routing bridge model, we are going to export all of our connectivity information, and that's saved as a PLM XML file that can then be read into NX. So, once we've exported our information, as we can see here within the NX environment, and our connectors have already been placed. Now, there are additional items here, such as your fixings and grommets, that aren't a part of your E3 project. So, what we're going to do, first of all, is we are going to define our spline paths, or our routing paths. This is where I could do with the video being a little bit quicker. So obviously we pass through our fixings, into our connectors. There we go. Okay, so we've now identified the route in which our harness is going to take. So what we now need to do is we now need to utilize the connectivity data that we have provided from E3 via the PLM XML file. What we're going to do now is we are going to go to import and bring in our created PLM XML file. So the PLM XML file contains information related to your connectors and obviously your connections. So next, what we're going to do then is we are now going to assign our components based on the information that is provided in our PLM XML file. So this is a manual assignment. There is the option for automatic assignments, providing that the information matches the information in the NX library as well. Could have done with a few less connectors. So once these have all been assigned, what we're then going to do is we're then going to look at the connectivity information. So in the next part, what we're going to see is we're going to see all of our connections. If we expand this, we then see that there is actually no length associated to this because they haven't actually been routed. So with a manual route at a component level, we then take into account all of our connection information, and it is then routed through the part. Okay. If we query any of these connections, then it will obviously highlight for us. So once our harness has been routed and all of our connectivity has been defined, what we need to then do is we need to export this part from NX, and we do that in the JT format. Now, within this, we do have to be mindful of the configuration and ensure that what we export contains everything that we need. Once exported, we can then load the JT file, or the native NX format file, into our 3D transformer. So on the right-hand side, we see all of the information that is contained in the JT file relating to our connections, our connectors. We're also exporting all of the fixings. And then what we're going to do is we're going to extract the topology data from this 3D model, which will then be used to generate our harness, or our flattened harness then. So there was a part there where we had to select to align fixings and grommets. Obviously, if you weren't using any fixings and grommets, then this could be ignored. Once we've extracted our topological data, what we can then do is we can then flatten our harness, and we do that firstly by selecting our backbone. If we then run the flatten harness, we see a 2D representation of our harness available to us. With a click to the icon to write to E3, the harness is then automatically loaded into E3 on a Formboard sheet. So what you will notice is when the 3D transformer creates our Formboard sheet, it doesn't place the table symbols automatically, so you will need to place these symbols manually. And obviously, if we were to query any of the connection lines, we then can see the segment diameters for those. So when we bring in the Formboard from the flattener, it is just a pure 2D drawing then, and this more often than not will require a little bit of work afterwards. So what you can do is obviously manually modify this to suit your requirements. So in our case, what we're doing then is we are taking any 90-degree bends and we're just angling these connections. We'll add our table symbols and any additional information we wanted. If we were then looking to add additional items, such as cable protection, this would be added at this stage as well. Okay? And our final harness would look as so. Excellent. Okay, so that's our round trip. So we're taking all of the connectivity information from E3, transferring it through to MCAD, performing our work in MCAD, bringing that back in its native JT format into the transformer, flattening and automatically generating our Formboard sheet. So next then is our outward trip. So our outward trip is the export of our connectivity, and there is no return to E3. Effectively, we are finished as soon as the PLM XML file is generated. There is the option for the outward trip with back annotation, in which the PLM XML file is updated and read back into E3 using the routing bridge. So outward trip, once again, sorry, a little bit too quick there. Okay, so obviously with the outward trip then, we've read in our PLM XML file, we've then routed our harness, and what we're going to do then is we're just going to export the connectivity information and bring that back into E3 via the routing bridge. So obviously we do an export from the routing bridge, but this time what we need to do is we do need to use the import function. So before the file is imported, we can query our connections, and we see there is no length associated with this. If we were then to import the PLM XML file using the routing bridge, once that's completed, we can then query the same connection again, and we see that our length information has now been populated into E3. Okay. So next then is the return trip. So this effectively starts in the MCAD environment, and then we bring that back into E3. So 3D is exported from NX in the JT format, read into our 3D transformer, flattened, and then a Formboard or a 2D harness drawing is generated. In certain cases, some customers may not have the electrification or the routing licenses, so the transformer will also handle non-electrified drawings from NX. Okay, and that's done with the option of the space reservation. But in these cases, what we do need to do is we do need to identify what is a schematic and the space reservation that we want. So in our case here, what we're going to say is across our connect lines, we are going to require a 5mm space reservation. And we then identify all of our connections. Once this is complete, we then export this information. Again, it's going to be a JT file. And this can also be read into our 3D transformer. Once read into the transformer, we can then flatten and generate our Formboard harness. Okay. So another option then available to us is, instead of exporting the 3D data from NX as a JT file, we can also handle a PLM XML file as well. So if all of the data is exported as a PLM XML format, we can then read that back through our additional module called the flattener. Okay? So this isn't the 3D transformer, it firstly goes through the harness flattener. Okay? From there, it can then be flattened and read back into E3 using the harness import option of the routing bridge. So outward trip as an alternative to the complete round trip. So connectivity goes out, and then the wire length comes back in. Okay, and again, that's the same with the PLM XML. We were to read the data rather than JT with the PLM XML. Sorry. Okay, so as with any integration between two systems, there are considerations to be made, and there are configurations and mappings to be obviously considered. So within E3, we can export a large amount of data. Okay, so through our configuration file or our mapping file, we can report the attributes of almost anything. But what we have to consider is what can be read by the MCAD system. So first of all, we ensure that we export only the relevant information. So this is an example of our control map, or our export mapping, and where you see all of the attributes, we can then build on those. So just ensure that you are exporting the information that can be read. This then goes through the MCAD format and importer, and the information, so in our case, that's all we're really seeing is our wire, cross-sectional area, colors, and the from and to information. Okay, that is then read into the MCAD systems. So there is another consideration if you are using 3DX or CATIA V6, that when we export the information, the 3D PLM XML, we do have to, the 3D XML file, we do have to ensure that we export it with authoring. Okay? Otherwise, certain attributes will be missing when we come to, obviously, transform and flatten this information. So within NX and Solid Edge, there is obviously a configuration for the JT export. And one of those considerations is we need to ensure that we get all of the CAD properties. Again, if we don't have all of the CAD properties, then certain information will be missed when importing back in through the transformer into E3. Okay. And finally, well, I say finally, what we also have to do is when we install the 3D transformer, there is a level of configuration that needs to be done before we can extract the topology. Certain information would be, any attributes. So how certain items are identified. What is a connector? What is a grommet? What is a fixin? Okay? And we do need to configure that before we can effectively bring the information from the 3D transformer back into E3. Okay? And as we can see here, the German colleague has his new configuration. Then once we have a configuration, we then see that the extract topology structure that used to be grayed out is now available to be selected. When you are configuring the 3D transformer, it is quite simple and quite quick in order to transfer rules from the transformer to attributed data. So for example, in our case here, we are looking at our fixin, so our cable tie fixin. So what we're going to say then is we are going to use the attribute for ECAD type of fixin. And if we wanted to copy that, what we can do is we can right click and we can select the copy attribute as object identification rule 4. And in our cases, we are going to say that this indicates that it is a fixin. Okay. Again, what we see then, string metadata, the value is fixin, which has been copied from the above. Again, we can only read correct information. So only correctly exported data can be imported from the PLM XML file. So if anything is unrooted in NX or in the PLM XML file, it can't be read into our transformer. So if we look at our PLM XML and using a PLM XML viewer, we can query the integrity of the data effectively. If something isn't rooted or doesn't have any relation to anything, it won't be considered by the transformer. We won't be able to do anything with it. Again, the same with any connections. If they are effectively unrooted, they will not be considered when we bring it in via the transformer. So, 3D transformer then is effectively a bit like a Swiss Army knife for us. It works for all of the software packages listed above. And our colleagues in Germany have also prepared videos for all of the software packages. So whereas I've only focused on NX this afternoon, if you would like to see more information how your mechanical CAD system would interface with E3, then if you obviously contact us, then we can arrange a time in order to show you this information once again, but using your MCAD systems. This has typically been an issue for us in the fact it's really hard for us to display anything in MCAD because unfortunately we don't have access to the MCAD, so this is a really good way in order to show you, rather than us just telling you, we can physically now show you how this functionality works with your system. Thank you very much.